Now let us see the cache memory organization. As discussed in the memory organization, that is in the memory hierarchy, the cache memory is the high performance buffer which is placed in between the processor and the main memory. Okay, and whenever we want any data, the CPU first refers to the cache. If there is a level 1 cache, first level 1 cache will be referred, and if the item is not found in the level 1, it will go to level 2. So then if there is a miss in the level 2 cache, then it will go for main memory. If there is a miss in the main memory, it goes to secondary storage. Okay, so here in order to reduce the effective memory, improve the cache ratio, that is the hit ratio. So more number of times if the data is found in the cache memory, then it is the total effective time will be less. So that's the reason we need to enhance the hit ratio of the cache. We discussed some of the problems related to the cache memory hierarchy, that's main memory hierarchy. Okay, and finding the effective memory access time, etc. Now let's see, so purely how this cache memory can be accessed. So what is the addressing required? Okay, that is how can we map the memory address to the cache memory address? Those are the important topics here. That is cache mapping techniques. Cache mapping techniques. Generally, when the CPU has generated a main memory address, okay, using this main memory address, we have to refer to the cache memory. Okay, this is the main memory address, for example. Main memory address may contain more bits, and the cache memory address may contain less bits. Say, for example, if you are having some 2 power 20 bytes of main memory, okay, and you are having only 2 power 10 bytes of cache memory, assume like this, then the cache address requires only 10 bits, but the main memory address requires 20 bits. Cache memory address requires 10 bits and main memory address requires 20 bits. So we need to convert this main memory address into cache memory address. So directly CPU cannot generate the cache memory address. CPU generates the physical address. Physical address means that is, even if you consider this virtual memory system, when the logical address is generated by CPU, that is converted into physical address. That physical address is equivalent to the main memory physical address, right? Okay, that physical memory address must be converted to the address of cache memory. That is, there must be a mapping between the main memory address and the cache memory address. There are different mapping techniques to map the main memory address. The main memory address we can store in the argument register. This argument register contains main memory address. We can also call it as a physical address. So when the physical address is generated, so that physical address must be mapped to the cache, because we have to refer to the cache first. When the data is not found in the cache, then we have to go to main memory. That's the reason cache memory must be referred. For that, the cache memory address we need to map. So main memory address we have to convert into cache memory address. For that, there are different techniques. This is one of the important topics in this memory system. Definitely the questions will come from this chapter, that is cache mapping technique. The first one is associative mapping. Associative mapping. Second one is direct mapping. Direct mapping. The third one is set associative mapping. Set associative mapping. Associative mapping, direct mapping, and set associative mapping. In these three mapping techniques, first to understand, okay, I will take one example of main memory, okay, and one example of cache memory. Assume we have taken a main memory of 32K into 12. 32K into 12. Okay, that means it is a 2 power 15 into 12. 2 power 15 into 12. So this is the main memory. 2 power 15 means there are 15 address bits. There are 15 address bits, and there are 12 data bits. 15 address bits and 12 data bits. So in order to represent 15 address bits, okay, we can go with some small notation, that is a binary coded octal notation. Let us see. That is a binary coded octal notation. Because every octal digit can be represented with 3 bits. 15 and 12 both are the multiplied with 3, multiples of 3. Like for example, if you have the first address 15 zeros, for example, this is the first address. 15 ones is the last address in binary. We can represent these addresses in the octal digits. Binary coded octal contains 0, 1, 2, 3, 4, 5, 6 and 7. This value 0, 0, 0, 0, 0, 1, 0, 1, 0 and so on, 1, 1, 1. Binary coded octal. That means this can be represented with 0, 0, 0, 0, 0, 5 zeros. 5 zeros means in the binary coded octal it will mention 0, 0, 0. This is 1, 0, 0, 0, 0 and 0, 0, 0, and each 0 is represented with 3 zeros. So total 5 octal digits. So 5 3s 15. So this is the binary coded octal address. The last address of this main memory system is 77777, because 7 is nothing but 111, 111, 111, 111, 111, 111. So this group of 3 bits each, because this is the total address, last address of the main memory. So 15 zeros is the first memory address, 15 ones is the last memory address. So that is represented with binary coded octal, just for easy reference. Every time we can't write the 15 digits, 15 bits, that's why binary coded octal. Binary coded hexa also we can take. If it is a multiple of 4, we can take that. Here just we have taken binary coded octal representation. Similarly, there is a cache memory in the memory system whose size, the cache memory whose size is 512 into 12. 512 into 12 cache memory. 512 into 12 means there are 512 words. That is 2 power 9 words. Each word is of 12 bits. So 9 zeros is the first address and the 9 ones is the last address for the cache. How can we represent these addresses in the binary coded octal? Group of 3 bits. This. Okay. So as the 9 bits, we can show with the 3 octal digits. That is 0, 0, 0 is the first address of the cache in binary coded octal, and 777 is the last address of the cache memory. So there are 9 address bits in the cache memory and 12 data bits. Data size is same. There are 9 address bits and the data bits are 12 data bits. Whenever the CPU has generated a 15-bit address, is nothing but the main memory address. It is not the cache memory address. Using the main memory address only, we need to refer to the cache memory. For that, we need to map. For example, 15-bit main memory address, we need to convert into 9-bit cache memory address in this example, because the cache memory size of address bits is 9 and main memory size address bits is 15 bits. Okay. So for this mapping, we are having different techniques. The technique is, first one is associative mapping. This is associative mapping. In associative mapping technique, cache mapping technique, whenever, for example, some data items of main memory are stored in cache. So what is the reason for having a cache here? In order to reduce the effective access time. That means the data items or instructions we have to keep available in the cache memory. Okay. So when the CPU has made a reference either for instruction or for data, we have to get that instruction, we have to get the data. So for that, we require to Okay, when the data item is stored in the cache memory, for example, okay, that cache memory data item must be stored along with its main memory address. That is what is associative mapping. Okay, because we need to refer to the cache first. If the cache is not having that referred data item, then we have to refer to the main memory. That's why we have to make a search in the cache whether that data item is available in the cache or not. Okay, if that is available, we can say it is a cache hit. If the item is not available, we can say it is the cache miss. So in that criteria, whenever there is a cache hit, we can refer it and access the cache, maybe for read operation or write operation. In associative mapping, whenever a main memory data item is kept in the cache memory, it has to be stored along with its main memory address. I will tell you with the help of an example. That is what associative mapping is. This is main memory, which we have shown, of 32K into 12 bits. And 12 address bits, how many are there? 15 address bits. We are representing with 5 octal digits. And there are 12 data bits. 12 data bits can be represented with 4 octal digits, because 4 3s are 12. Okay, 12 data bits can be represented with 4 octal digits. So now here, for example, these are the addresses. Somewhere from 00777 at this address, there is a data 1423. Okay, this is a main memory address, and this is the data stored in that location of main memory. And somewhere in the address 10173, there is an address. The data stored is some 3257. And some at address 77000, there is a data that is some 1415. This is the data represented in octal only. And at address some 77, okay, 107, this is the octal address. In this address, there is a data item 1056. Okay, and some other address 77777. Okay, at this address there is a data some 4762, like this. These are the data items available at different locations of main memory. So some of the data items you wanted to retrieve into the cache in order to improve the hit ratio. So this is the cache. Whenever, for example, you have stored some item, let us suppose this data item, and this data item I wanted to store in the cache. Assume that those are important data items. Okay, then 3257, that is one data item stored. Again, one more data item is 1415, that is another item, and also 4762, this is another data item. These data items are stored from the main memory to the cache. Whenever a data item is stored in the cache memory, in associative mapping, what we have to do is, we have to store these data items along with its main memory address. We have to store these data items along with its main memory address. Okay, so for storing the main memory address, some extra associate memory is required. So this is the data, and associated main memory address respect to the data is 3257 is in which main memory address? 10173. This is the main memory address of this data. And what is the main memory address of this data 1415? It is 77000. and 4762, the main memory address is 77777. So few of the data items we have stored. Okay, and for example, the cache memory has some CPU has generated some address 77107. 77107 is the address generated by the CPU, which is the main memory address. This is the argument register. Argument register contains the main memory address. So the main memory address says that 77101. If you go to directly with the main memory, so you will get the item. So that is a hit for main memory. But when the cache memory is there, first you have to go to level wise. First you have to go to the cache memory. So this is the cache memory. Okay. So in associative mapping, whenever a data is stored in the cache memory, the data is stored along with its main memory address, right? So now it has to make a search for all the locations of the cache. Okay, like 77101 matched with 10173, not matched. Again 77107, it is matched with 77000. This address is also not matched. This is matched with 77777. So no address is matched. So this address is considered as a cache miss. This address is considered as a cache miss because the CPU wants the data, that is what is that? 1056 is the data required for CPU, that is not available in the cache, that is considered as a cache miss. Okay. So in order to implement this associative mapping, we require to have a associative match logic buffers. Okay. So this match logic implementation, it is possible in associative memory. Okay. So that each address generated by the CPU must be matched with the addresses, and also the cache can store in each address only one data item can be stored, but where the address can be stored, separate memory is required for storing the main memory address in the respective location. So we require to have a separate memory for storing the main memory address in addition to the cache. In the cache mapping implementation, we require to have a separate memory for storing the main memory address in the separate memory when the data item is stored from the main memory. Okay, no data item will be stored without having a main memory address. It is very difficult to identify. So that is a disadvantage of this associative mapping. The main disadvantage is whenever any data is stored in the cache memory, the corresponding data main memory address also must be stored in the cache in a separate memory location. That is some extra memory is required for that storing the addresses. Okay, whenever an address is generated by the CPU, so like this in the argument register, that address must be compared with every address. If match is found, that is considered as hit. If match is not found, that is considered as miss. When there is a miss, next time we can retrieve it. For example, now it is miss, I wanted to transfer, so I refer to, if a miss is there in the cache memory, I refer to main memory. Yes, it is hit. So in that case, now 1056 item we will store in the cache, and respect to main memory address also will be stored, so that next time when you refer once again, no, so there won't be any miss. For example, right now this argument CPU has a requirement of data, that is 4762, and address generated by the CPU is 77777. Okay, this is the main memory address, and this must be compared with every address in the cache mapping. That is 77107 not found, 10173 not found, and 7700 not matched, 77777. So it is matched. So there is a match. So this match logic is implemented in associated buffers. Okay. So this is considered as a cache hit. Earlier it was cache miss. Now this is considered as a cache miss. Okay. So when there is a cache miss, so directly a cache hit is there, directly we can retrieve the data. When there is a cache miss, we have to retrieve from main memory, and the same thing to be loaded in the cache along with its main memory address. So like that, the associative mapping is implemented. Associative mapping is just a small base technique in order to implement the cache memory from main memory addresses. So this is one of the mapping technique. So in order to overcome the disadvantage of this associative mapping, because whenever the data is stored, we have to store the entire main memory address. So for data, how much memory is occupied? 12 bits. For main memory address, how much memory is required? 15 bits of address. For example, 4 data items are stored, 4 into 15, 60 bits are required as an extra memory in the cache controller. That's the reason we can have some other alternative techniques in addition to this associative mapping. You can just note down this. We can have some other alternative techniques like direct mapping and set associative mapping. Let's see direct mapping. In a direct mapping, without storing the entire main memory address, we can directly able to refer to the cache address location using main memory address only. So the main memory address we will divide into different parts. Main memory address is divided into different parts in the direct mapping. Let us see like this. Direct mapping. So when the argument register has a 15-bit address, how many bits will be there in the main memory address? 15-bit address will be there. This 15 bits main memory address will be divided into two parts. One is the tag, other is the index. Tag and index. This index number of bits is equal to cache memory address bits. So there will be 9-bit index and the remaining bits will be used as tag. The tag is remaining 6 bits. 9 bits index and the tag is 6 bits. Okay. So for example, this is the main memory. This is the main memory, and let us see some reference. Okay, that is 32k into some 12. Okay, this is main memory locations, and we are having addresses 000002 77777. This is the last address, and this is the cache memory. We are referring a size of 512 into 12. 512 into 12 cache memory. This is 2 power 9 into 12. So there will be 9 address bits. 000 is the first address. The 777 is the last address. So as and when any address is generated, it will be divided into two parts. For example, the address is something like 77777, for example. This is an address. For a 6 bits, how many octal digits? 2 octal digits. That means this is indicating the tag of that address, and this is indicating index of that address. This is indicating tag of that address. This is indicating index of that address. So using this index of this address part, we are able to refer to the cache address directly. That's why it is called a direct mapping. In this address, when the argument register has this address for the cache, okay, we can directly go with this index. So the least significant 9 bits is indicating index, so directly we are able to go to 777 using this index. After going there, whether the corresponding tag is there in the control route, we have to check whether this address or data belonging to the similar tag or not. So like that, we can refer to the cache memory directly. So how you are dividing here now? How many bits must be used for index? Number of bits in the index part should be equal to number of address bits of cache. Note on that point. Number of bits in the index is equal to number of address bits of the cache. So that we can directly go to that address. Number of bits in the index part, in the index, is equal to number of address bits. Number of address bits of the cache. Number of bits in the index register is equal, index part of this address is equal to number of address bits of the cache. I will show you with the help of an example, okay, how the data items are referred using this direct mapping, and also what are the advantages and disadvantages of the direct mapping. What are the advantages and disadvantages of the direct mapping? But it is better when you compare this with associative mapping. When you compare this with associative mapping, this direct mapping is better, because we are able to directly go to the cache memory without storing the entire address of main memory, just like associative memory. For example, this is the main memory. This is containing different data items at different locations. This is the main memory. Main memory may be 00000. The data is 1241. Is a 12-bit data, and at some address 00777, there is a data 4357. Similarly, at some address 010007413, We can't show number 8 in the data or in the address because 8 is not a valid binary octal. Okay, then 01777, there is a value 4312. Okay, and again 77 some 000, there is a value 6124, and 77777. At this address there is a data some 6472. These are the data items available at the different locations of main memory, and this is the cache memory. In the cache memory, what we do is we have to store in the cache controller the tag value also. Whenever any data is stored from the main memory, okay, the respective tag number also must be stored, because the main memory address is divided into tag and index. Main memory address is divided into tag and index. So this is the tag value and this is the index value. Using index we are referred to the cache. So what are the cache addresses here? Cache addresses as 000 to 777. Let us assume the index is 00 I am showing, index 777 I am showing. So related to index 000 I am storing 1241 for example. The data, this is the data of the cache and this is the tag of the cache. So 1241 is the data related to the index, but what is the tag of this? First 2 digits are tag and the next 3 digits are index. Because the 6 bits is the tag in the 15-bit address, first 6 bits is the tag, 6 bits means 2 octal digits, next 9 bits is index, that means 3 octal digits. Okay, and what is the tag corresponding to this? 00 is the tag in binary coded octal. For example, we are storing some 777, this address for example 01777, the data is this, these two data items we stored. 4312 is the data, and what is the corresponding tag value? Index is 777, the tag value is 01, so the corresponding tag value must be stored. Tag is referring whether this index is belonging to the same data tag or not. Okay, for instance, let us suppose the address generated by the CPU is something like 77777. So this is a physical memory address. First what it does in the direct mapping, it will divide this address into two parts. This is the tag, this is the index. Using this index, it is directly going to that location of cache, because index says that go to 777. So we are able to map the cache address directly using main memory address. At the same time, at this location, whether the tag is matched or not, you have to check. So what is the tag here? 77 in the generated address. What is the tag stored corresponding to this index? 01. That means this data item is not belonging to 77777 main memory address. This is belonging to 01777. So that this will be considered as a cache miss. This will be considered as a cache miss. For example, if the address generated by the CPU is 01777 for example, 01777. So this is index. Using this index, it is going to the same address. But what is the tag value that is generated in the address? 01. What is the tag value in the controller? 01. So for storing the tag, extra memory is required, because in one location we can have only one data item. This is for this extra memory is required in the cache controller. Okay, for each location 6 bits extra memory means there are 2 power 9 locations. Each location is having 6 bits, 2 power 9 into 6 bits of extra memory is required. Okay, now this 01 will be matched. That is nothing but this is considered as a cache hit. This is considered as a cache hit. Okay, when there are two addresses, both are having different tag numbers, but their index is same. There are two addresses, both are having different tags, but their index value is same. One is a miss, one is a hit. That means we cannot store the two data items from the main memory whose index is same and the tags are different. There is a disadvantage of direct mapping. Note on that point. We cannot store two data items from the main memory whose index value is the same and the tag values are different. Whose index values are same and the tag values are different. For example, we are having 01000. Similarly, 77000. So this is two addresses. This address and this address, both addresses are containing index value same, but the tags are different. So if you go to the index 000, either only one tag can be stored. That is, we already stored the 00 tag information. We can't store either 01 tag information or 77 tag information. So related to one index, only one tag information we can store. Multiple tags we can't store for the same index. That's why two data items from the different locations of memory whose index value is the same, okay, and the tags are different, we can't store. Only one data item can be stored. So here we are having three of like this 00000 also containing the same index. Out of three, only one tag we can store, either 01 or 7700. 00 is already stored. Next time if you wanted to replace, then the tag will be replaced with 77 if that data item you want. Next you want to tag 01, that 01 will be replaced. That is a disadvantage of direct mapping. And advantage is we are not searching. In the previous example of associative mapping, we have to make a search. Here no need to search. Directly we are going to ith location of cache if it is ith index. Okay. But in the case of that associative mapping, with the generated CPU address, we have to compare each entry and it is found or not, match is there or not. Okay, if match is there, it will be considered as hit. Otherwise, we have to search and we have to implement the match logic. It takes little bit extra time. Okay, so when compared to main memory access time, all these things will be less only, but still it is more time when compared to this direct mapping. So this is the difference between associative mapping